Assalamu alaikum. Today I will discuss with you how to design the gains of the PI speed controllers. So here we'll discuss how to design the gains of the PI speed controller. Now if you recall, if we are using the closed loop V over F control or the field oriented vector control, we need a PI speed controller. So in general, one question is how to design the gains. For that, I will use the closed loop vector control, and I will start recalling. TE was equal to 3p over 2 RR dash over S omega S Vs square over RS plus RR dash over S all square plus X LS plus XLR dash all square. Now here I use the electrical synchronous speed rather than the synchronous mechanical speed, and which is related by P over 2. Now at normal operation condition, which mean the slip is low, or at low slip, the torque can be approximated as. Now at low slip, this term is greater than this term. So the torque can be approximated as 3p over 2 RR dash over S omega S Vs square over RS plus RR dash over S all square. Now the same at low slip, this term is greater than this term, so the torque can be approximated as T equal to 3p over 2 RR dash over S omega S Vs square over RR dash squared over S squared. Now this can be written as 3p over 2 1 over RR dash Vs square over S omega S S square. So simply here, one of the S's will eat one of the S's there, and TE will equal to 3p over 2 1 over RR dash over here RR dash square. Oh, sorry. That's correct. Yep, this one here, and I will end up with Bs square over omega S S. If I multiply here omega S, this will be omega S square. So now TE will equal to 3p over 2 1 over RR dash Vs over omega S all square S omega s. Now, if the ratio Vs over omega s is kept constant, then the torque can be controlled by controlling the slip speed, can be controlled by controlling the slip speed. So simply to this end, this means that Te is equal to 3p over 2 1 over rr dash Vs over omega s all squared s omega s. Now we know that this term is omega slip. And if we make the ratio of V over omega to be constant, which is the case in the constant V over F, then this term is constant at constant flux. So simply this means that the torque is proportional with S omega S. So simply this means that the torque can be written as constant Kt S omega S. Now how to find the constant? Simply Kt will equal Te over S omega S at rated condition. So now we have a relation between the torque and the slip speed, and the output of the PI control is the slip speed. Now if we write the swing equation, which is J d omega by dt plus b omega is equal Te minus TL. Here I'm assuming a motor action. Now in S domain, or taking Laplace transform, this will read as J S plus B all multiplied by omega of S equal to Te of S minus TL of S. So solving with respect to omega of S will equal to Te of S minus TL of S over Js plus B. And remember, we have a relation for the torque, Te of S equal to Kt S omega S. Or we can write it in terms of the slip speed equal to Kt omega slip. So here, if this is omega reference, and if we are comparing this one with the actual omega, then we are using a PI control. This is Gc of S, which is the PI speed controller. The output of the speed controller is omega slip. So if we multiply this one by Kt, we are getting Te. If we subtract this one from minus TL, then we are multiplying by 1 over Js plus B. We are getting omega and this will close the loop. So this is a closed loop. Of course, it's a simple representation of a linearized version of the V over F closed loop control. Now, GC of S equal to Kp plus Ki over S, where P is the proportional gain and Ki is the integral gain. Now this can be written as Kp S plus Ki all over S. Now here we have two gains to design, which is Kb, Ki. Sometimes it's better to write the controller in terms of gain and time constant. To do so, Gc of S can be written as Ki Kp over Ki S plus 1 over S. Now, if we multiply here by Kp over Ki and here Kp over Ki, we'll end up with Gc of S equal to Kp over Ki S plus 1 over Kp over Ki S. Now let K equal to Kp and let's say Kc and the gain of the controller, and tau c, the time constant of the controller, will equal to Kp over Ki. So using the Kc gain and the time constant, the Pi control can be written as Gc of S equal to Kc tau c S plus 1 over tau c S. Now the Pi control here is represented by a gain and a time constant. So now the mechanical system of the machine, which is, we can call it here, this one, I can call it Gm of S. So Gm of S, which was equal 1 over Js plus B, this can be written in terms of gain and time constant as 1 over B J over B S plus 1. So Gm of S is equal to Km over tau m S plus 1, where Km is equal 1 over B and tau m is equal J over B. So here again, we are writing the mechanical system of the machine in terms of the gain and time constant. So let's recall the block diagram. So this will be the reference speed, a comparator, it's minus omega. This is the error signal that will go through Pi speed control. He will write using a gain and time constant. And here is omega slip. If we multiply it by Kt, we are getting the torque Te. Now here we are assuming we have the load torque, which is in general unknown disturbance, and this will be the mechanical part of the machine, which we wrote it in terms of DC gain and time constant. k m over tau m s plus 1. This will be omega, and this will close the loop. Now, simply the closed loop system is of second order, is of a second order. Let's correct this one here. Tau s, and this is c, huh? Tau c. Tau c of s. Yep. Now, one method to simplify the design is to design the gains of the BI control such that tau c is equal tau m. Now, if the case, this will be the famous zero pulse cancellation. This will be the zero pulse cancellation. And here we can do that because the cancelled ball is stable. So if this is the case, then this zero will cancel this ball, and we'll end up with omega star minus omega here. Here we'll have kc over tau c s. Here is kt, and this is the load, and here we have constant, which is the km, and this will be the shaft speed, and this the closed loop. Now here, using the zero pulse cancellation, the system become first order. Now to find the closed loop system, it's very simple. It's actually a cheesecake, easy to be eaten. Huh? It's very simple to do that. So simply here, if I need to find the closed loop transfer function, we don't need to go to the Mason here. Simply, it's a very simple block diagram. It's actually the famous feedback connection. So this will be the G open loop, which will equal Kc Kt over tau C S multiplied by Km. So the T of S, or let's use G closed loop. So G of the closed loop will equal G of open loop over 1 plus G of the open loop. So G of the closed loop will equal to we stated that it will equal to Kc Kt Km. So Kc Kt Km over tau C S over 1 plus Kc Kt Km over tau C S. Now if we multiply G of the closed loop of S will equal to Kc Kt Km over tau C over S plus Kc Kt Km over tau C. Now, one observation here, the DC gain is equal to 1, and I will recall the DC gain of a transfer function is equal to GCL of S at S equal to 0. So simply G closed loop of s can be written as k over tau s plus 1, where k is the closed loop DC gain, and in this case k is equal to 1. Alright, here G closed loop is equal to of S is equal to k over tau S plus 1, where k is equal G of the closed loop of S at S equal to 0, which here it was kc km kt over tau c over kc km kt over tau c, which equal to 1, while tau, which is the time constant, the closed loop time constant, is equal to one over kc km kt over tau c, which equal tau c over kc km kt. Now, we know that we cannot change tau c because by assumption we are using the zero bus cancellation, so tau c is equal tau m, which equal the j over b. So this one is fixed. So how we can modify the transfer response? Here it's first order system, and the system is characterized fully by a DC gain and the time constant. The DC gain is equal to 1, which means that the steady state value is equal to the reference value. And tau is a measure of the speed of the response. So here how to control the time constant of the closed loop system. Fortunately, here we have what? We have Kc is the remaining degree of freedom that we can design in order to specify a specific closed loop delay time constant, let's say. So simply here Kc can be designed to get a desired closed loop time constant. So now we have a systematic procedure in order to design the gains of the PI controller. So simply stay home, stay safe. Good luck and hope to see you soon.